Hello everybody! I hope everyone's having a wonderful day. So today is going to be the final lecture for Computer Science 128. So I thought today I would just kind of summarize a lot of the key concepts that we've been talking about throughout the term. Now, this isn't going to be everything, but I just want to kind of go through some of the things that we've talked about and kind of hammer in those main programming ideas. I thought it would be pretty valuable just to do that. And I also wanted to make sure I did something so that maybe we could kind of tie everything together. Because throughout this class, we've been kind of taking in bits and pieces how we could solve different problems through ultimately using multimedia approaches. So for example, manipulating pictures, sounds, strings, all sorts of different things like text. We've looked at various different problems we can solve using programming. I want to kind of take the opposite approach just to kind of reinforce things that we've talked about throughout the term. So that's going to be the plan today, and I'm just going to kind of take us down this road. So I'm going to remind you what a variable is and a name is, and then we're going to talk about functions briefly. Then we're going to talk about control structures, so a lot of the ones we've seen, and then I'm going to give you examples of each one, and ultimately where things go from here. So anyways, let's get going. So remember that in programming, whenever we have a value, when we want to store it and use it, we ultimately have to give it a name. So functions can have names, variables can have names, and variables have different types. So for example, some of the main types we've seen are integers, floats, and strings in Python. Now remember, ultimately down the line, these are all eventually inside the computer coded as bits. So as bits of information. We'll come back to that fact a little bit later on again. So remember, whenever you want to assign a variable some value, you have to use the equal sign, which represents assignment. It is not equality. We'll talk about what equal to means in Python in a little bit. So for example, if I have a variable called myVariable and I want to assign it the value 5, I can go myVariable assigned to 5, just as I have it here. So a function, remember a function has a name and has parentheses that follow the name. So these act as parameters inside the parentheses. So these inputs, there can be 0 or more inputs. And these provide information that changes slightly the behavior of the function for whatever goal or process or purpose the function may have. So remember, it takes 0 or more possible values as input. Sometimes we call these parameters. And these are given to the function to perform an operation. So imagine it like my machine. Remember the machine I drew on the board? There's the machine. So I have my inputs, I feed them to the machine, and it's called some function. That's the name of this machine, and it does stuff. It just does stuff. I don't know what it does, but it does stuff. Sometimes I know, sometimes I don't know. And it produces output. So this output can be, say, printed to the console, or it could literally be where it returns a result. So remember, those two things are different. I'm going to talk about that in one moment. So remember, whenever we're programming in Python, remember that the keyword def indicates that we're going to define a function. So if we ever want to use a function, we need to call it. So that means that if I give you the definition of a function, that tells you the cookbook. So this is the recipe, and it tells me how I'm supposed to follow the recipe. Calling the function is saying, hey, look, let's actually do the recipe. And I'm going to give you my ingredients so that I can do the recipe, right? I've used this idea before. So that being said, I've given a couple examples of functions here. I first have one called sum. It takes in 2 variables here. It has num1 and num2. These are intended to be numbers. And what happens is sum is it returns the sum of num1 and num2 versus the other function called sumPrint, which takes in intended two numbers, num1, num2, and it prints the sum of num1 and num2. So it should be very important to note that a function returning a value is not the same as printing that value to the console. So just to illustrate this, you'll notice that if I call sum, it will return to me the resulting sum of those two numbers that I give it. Remember my picture with the machine. If I give you sum, it's taking as inputs two numbers. It goes into the machine. Sum will add the two numbers, and then it returns, so it spits out for me to use it, the sum of those two numbers, which is just the purpose of sum. So this is in contrast to the function sumPrint, but you'll notice it doesn't return anything. This one actually, out of technicalities, if you try to check and see what sumPrint returns, in Python it'll return none, because it doesn't return anything. So technically it doesn't return anything, but when you try to use it, it gives you none, because it doesn't return anything. By default, it has nothing to return. So sumPrint here will just print. It prints to the console. So remember, these are not the same thing. So when I execute this code I have over here, I end up getting it where it prints out 18. Because because sum is given as inputs 8 and 10. And then it adds the two numbers, then it returns back it, and then I assign result to be the resulting value of sum, which is just going to be 18. So result is going to be assigned 18 after sum is calculated. And then it prints 18. Now, versus sumPrint, you'll notice that it literally just prints 20 to the console because it's given as inputs 10 and 10, and it adds those together and prints it. So just keep that in mind. So remember, when you want to define a function, use the keyword def. Now, one thing that's worth noting is, remember, in Python, indenting does matter. So whenever you indent by pressing tab or using, I think it's a few spaces, if my memory serves me correctly, that will create an indent, and anything within that indent is treated as its own code block that belongs to the structure that is above it. And these are naturally either functions or other control structures. So let's talk about those control structures. So the first one I want to talk about is the if statement. So one of the most fundamental ones. So if I give you some program and I want to branch the flow of execution, I want to normally do it on some logical test. Now remember, logical statements are either true or false. They can't be both. They can't be both true and they can't be both false. They're either true or false. They must be testing the true or false, but not both or neither. So naturally, when you have the structure of an if statement, you'll have if, and then right after that, you'll indicate your logical test. So wherever I have the square brackets, that's where your code would go. And then I have colons in Python. Remember, colons are very important because if you don't indicate the colons, the Python interpreter will not be very happy. So remember, the same thing is true when we're talking about functions. When I define a function, I give after the parentheses, I make sure I include a colon. So I have my test, and then I indent in, and then I have my block of code. Anything that's indented in will be a part of that block of code that executes only if that test passes. So when you construct a logical test, you can use comparisons. So for example, less than, greater than, less than or equal, greater or equal to. Remember, equal to is not the same as assignment. Equal to is two equal signs. And not equal in Python is the less than and the greater than symbol together like a diamond. A lot of programming languages beyond this class, you might encounter it where it's actually an exclamation mark, then an equal sign saying not equals. So programming languages like Java do it like that. So likewise, if you ever want to combine tests that are using comparisons like this, you can use logical connectives, not, and or. So just to walk you through this example, say, for example, I have here a variable I've declared and I've assigned it the value 6. So I've initialized x's value to be 6. Then I proceed to my test here. So I have my test over here. So the test over here is going to check if if at least x is greater than 5 or x is less than 1 is true. So it has to be one or the other or both. That's what OR is going to do here. So it's not an either or, it's an inclusive OR. So it means that at least one of those two things must be true. Both can be true, that's okay. And in this case, you'll notice that 6 is greater than 5, so we know that the code inside of the block associated with that if statement will execute. So it means it will assign y to be x plus 1, but remember x is 6, so y is going to be assigned 7. And then it's going to print 6 to the console because x is 6 at this point, right? But so after that's finished, notice that the next code after that, it proceeds to this next if statement, which is outside the block, right? So note if the test failed, say for example, if x was equal to 3, let's go with x is equal to 3. If x was equal to 3 at the beginning here where I assigned x to be a number, if I were to assign x to be 3, you'll notice that the first test here with if x is greater than 5 or x is less than 1 will fail. So none of the code inside of that if statement will execute. And it will proceed right to that next line after that block. So then it will be right at if x is equal to 2. Now, if x is 6, then it's not equal to 2. So that code inside of the block where it asks to print x will not execute as 6 is not equal to 2. Notice that the last statement I have here, a print command, this print command will just simply work regardless of the result of the test, because remember, it's not a part of the code block that's associated with that if statement. If I indented that in, that last print statement where it prints out end is reached to the console will not occur. But it does, because remember, it's not indented in. It's not a part of that if statement. So remember, I have if, some logical test. If it's true, it executes the code that's in that block that's associated with the if statement by indenting that code in. So likewise, if ever an if statement's test fails, we often want it to do something else. Usually, like I said in class, we have it if this happens, otherwise do this. Do this something. So let's think about this. So the else statement is what we're going to talk about here. So we talked about this in class. So the first thing I should note is an else statement always must follow an if statement. So if I give you some if statement with a logical test, if it passes, it executes the code associated with that test, right? Indented in. Now, if it fails the test, we need some way to make it so whenever that doesn't happen, the other code happens. That's the purpose of the else block. So right after that, you'll notice that I have my else. It follows the if statement, and it will execute if the test fails. So it's a nice way of formulating if X happens, do X, otherwise do Y. So here's an example. I've given you a function. It's called parity length, and it takes in a string, and it's going to print odd or even, depending on the length of the string, my string, which, remember, my string is input for the function. Remember, in Python, it passes it by reference to the function. So remember, it's given to the function to operate. Some programming languages will literally copy it in, depending on their types. Some will literally copy by reference. So remember, we talked about that in class. Remember, that was our analogy where I was drawing the arrows on the board, where I was talking about how pixel objects, I can't just pass a pixel along to somebody and give them that reference and expect it to be like it used to be. If I start tweaking around with its color components, because I already gave them the reference to it. I didn't copy it, I just gave it to them. So the point I'm getting at is that I have a function called parity length. It takes in a string. I have an if statement. I check if the length, remember the length function here will determine how long the string is. And it's asking if my string is even. Now remember, that's the modulus right there with the percentage. And it's just checking if mod 2 is equal to 0. Remember, that's just integer remainder. So if I give you a number and I divide it by 2, and I'm asking if that will be an integer or not. If it's an integer, then it's divisible by 2, right? So if that happens, it prints out even. Otherwise, we have our else statement, and the code inside of the else block is going to print odd to the console. So for example, if I give it parity length and I give it a string hello, hello has 5 characters in it, then it's going to print odd to the console. My apologies. I got a little ahead of things. I should explain. So on my screen over here, I have all my capturing stuff, and over here I have my screen and along with the camera here that I'm talking with you with. Whenever I switch a slide, I have to click to indicate the change. So I apologize for that. So let me just reiterate this because it wasn't on the screen. So just to reiterate what I said before, just a little quicker. Remember, else statements, if I give you a test, I want something to operate otherwise if it fails. So that's the purpose of the else statement. So I put my code inside of the else statements block, like I have here on the screen. And if it's so, if the test fails, it will automatically execute the code in the else. That's under, of course, the assumption that I don't use an Elseif statement. So sometimes you have multiple tests. So sometimes you have branching behavior where you have a test, and that test might pass or fail. But you might also have another condition you want to check, another test. But it depends on the previous test. You want to make sure if that test fails, that you check your second test to see if it's actually correct or incorrect. So this is the purpose of an else statement. Imagine you have some behavior you want to branch multiple different ways, but you have multiple tests, but each one depends on the previous one. So this is normally noted in Python, it's elif, so it's Elseif. We can have as many of these elif statements as we need, but remember, there still has to be an initial test that is denoted with an if statement. So an else block worth noting, because remember I can have, actually let me first talk about the structure of this. So I have if with some logical test. If it passes, it executes the code associated with that test inside the block. Otherwise, if, so remember whenever we talk about else if, you can think of otherwise if this is true, then you're going to execute the code associated with that test. So, but the first test had to fail first. If I wanted more than one of these to execute, I would just use if statements instead of else ifs. So I would have else if, otherwise if this test passes, then execute that code. Otherwise, if it doesn't, then I go to the next else if, and then I go to the next else if, etc., etc., etc. I can optionally include an else statement at the end and include a block if none of the tests above it passed. And it just operates the same way. The only difference is, of course, it only executes if all of the tests failed above it. And then any code that happens after, it happens after. As long as it's not a part of the code block associated with the else if or an else, respectively. So here's another example. So imagine I have x is assigned 3, y is assigned 2, and I ask a question. Is x plus y equal to 5 and x minus y equal to 3? Now notice that I'm using the word and there, so it's a logical connective or a logical operator and. It must be that both x plus y equals 5 and x minus y equals 3. Both of these have to be true for this test to pass. Because and means this and that. Just like if I really wanted to have pizza and ice cream, I want to have pizza and ice cream. I'm not compromising on any of them, right? So that being said, if that were the case, it would print out x plus y. But notice here that 3 and 2, if I add those together, I get 5, which is true, right? However, if I take x minus y, that's 3 minus 2, which is equal to 1. So this if statement test will fail, meaning it's false. That test, that logical test is false. It results in false. I should be precise. So thus the test fails. And thus it doesn't print x plus y. And it proceeds right immediately to the elif of checking y is equal to 2, which it is, right? So it prints out y to the console, which is 2, right? It prints 2 to the console. And now, if for example, I gave you a y that failed in circumstances with an x, such that that first test failed and the elif test failed, like say if y was equal to, I don't know, minus 20. Say it's minus 20. You know it would fail both the first and the second test. It will go immediately. It will proceed to the else block there, because it will go to the else statement, and it'll print out x. But remember, I already passed one of my tests, so I never have to consider that otherwise, right? So that being said, I don't ever consider the code after the inside that else block there. And then regardless, I print out end is reached because it's not associated with the code block, right? So that's ifs, elifs, or elseif, and else. I want to talk about loops. So in this class, we talked about the concept of a for loop, or in Python or Jython, it's called a for each loop. So remember, you're given some collection. This could be a string, could be a list. And we consider each element in the collection. So for example, we consider each character in a string, each element in a list, So this is generally the way a for each loop works. It goes through the collection, it goes through one after the other. So this is just the general structure of a for loop or a for each loop. So I have for, and then I have a name for a variable, which is going to be set the next object or element in the collection. Each time I go through the loop, one after the other, getting each one successfully in the collection. So the collection is just some string, it could be a list, it could be a range function, which gives me a list of numbers. So that var, whatever I call var, like position or value or var, whatever, could be a useful name. Remember, you want to find names that are meaningful for your programs. So keep in mind that if you're doing this, make sure you pick a meaningful name for your variable so you can use it and it makes sense to the reader. So when I do this, I consider each element in the collection, and for each one, it executes the code inside the for block here. So all that code that's indented in below the for there will get executed once for each element in the collection. Each one of these executions of the block and then coming to check the condition is called an iteration of the loop. So for example, if I have 5 elements in my collection, then my loop will probably perform 5 iterations, one with each element in the collection. So here's an example. I have a function called MultiList, and it returns the product of all the numbers in some list called SumList. So I'm going to start off with, so I'm just going to make one assumption with this. I'm going to assume that the list has at least one element in it. So I'm going to start off by assuming that the resulting product will be 1. It's a nice default value to put in there. If you really don't like that, you can always just start off by giving you the first element in the list and then just disregarding one extra element somewhere. We've done this trick before, but I'm just giving you some ideas. You don't have to do it this exact way. There's a lot of different ways you could do this. So I can go through for pos. Pos is going to be the variable that's going to take on each element in the collection. In range, now remember the range function has many different versions. It has at least 3 versions. If you give it one argument, it counts as the end index, and that end index is exclusive. If I give it the length of the list, remember len, when I give it a list, it tells me how many elements are in the list. So this will go from 0, 1, 2, 3, 4, all the way up to the length of some list minus 1. Because it won't include the number that is the length of some list. Because remember, it's exclusive. It counts up to it, but not it. So the resulting range function gives me a list of these possible indices that I can index. And then all I'm doing is I just go from I'm just going to take product and I'm going to multiply it by each element that's in the list. And I'm going to index into each one using square brackets, using pos, because pos tells me what location each one of these elements is going to be in the list. And then I just simply return the product. It seems pretty straightforward, right? So here's another example. And I thought I would give you something that probably would be very helpful for you down the line. I thought I would consider the example of if I gave you a bunch of comma-separated data. Now, this quite often happens in the sciences or the engineering stuff. You very often have it where you have a whole bunch of data, and it's given to you in like a string. And you need to take all the bits and pieces out of these strings and get the data out of them, or analyze that data. So this function is in the following way is going to be given a string. It's going to be formatted in such a way that is called comma-separated values format. So it means that, and keep in mind, this is pretty common among spreadsheets and raw data that's usually stored compactly. So for example, when people record things in spreadsheets, oftentimes they store them in comma-separated value format. In fact, in Excel, you could, for example, save things in this format. It's called CSV. So imagine you wanted to take a line of data and say this stuff was just integers. What I want to do with my functions, I want to get given a string that contains the comma-separated value data. So it's just a string of numbers with commas that are separating them. And I want it to return to me the sum of those numbers. So oftentimes when you're doing research or something like that, or you're trying to collect up data, for example, you might often, for example, try to store these in a list so you can do manipulations. In our case, we're just going to keep it simple and just try to add the values in them. So here's my function. It's called sum numbers, and it's going to take in a string I'm going to call numString. So I'm going to assume that the sum is going to be 0. And then what I'm going to do is I'm going to use my split method for the string. Because remember, split, what it'll do is it takes the string and it chops it up over a special character. Now, keep in mind that if I give it nothing, it assumes just a blank space is the special character. So if I had like 4 space 3 space 7 space 10, it will split those strings into characters or substrings, or just strings that are split up into pieces, kind of like a long piece of pepperoni and you're trying to cut it up into pieces. It's going along and kind of marking out all the spots where you need to cut them up so that you can have some pepperoni. So the point I'm getting at is that here I'm going to be using split, and I'm going to have a comma as my special symbol. So because all my data is going to be split up over commas. So if I use split and I give it, say, for example, a string with 3, 4, 3, 10, all separated, all with commas in between them, like that, it would give me back a list containing the string 3, the string 4, the string 3, then the string 10. So I've called this list tokens because you can think of each one as like a token. Kind of like when I cut up the pepperoni, each one of these pieces of pepperoni might look like kind of like a token that I could give somebody. Pepperoni is a pretty good currency, right? Anyways, the point I'm getting at is that we want to consider now each one of our tokens, each one of our elements in that list of strings. So I'm just going to go for lm. lm is going to be the variable that's going to occupy each one of these strings that I'm going to get from the list of strings called tokens. So I get each one at a time. And now what I want to do is I want to include this in my sum, right? So I'm just going to take my sum and I'm going to add to sum itself. Like, obviously I should rephrase myself. Be very careful with this. So I'm going to assign sum to be itself plus the value of lm when I convert it to an integer. So when it's a string that looks like 3, I need to make it into an integer that is 3, right? So I need to use the function int to convert it from a string to an integer. And then I can include in my sum. And I'm just going to add up each one, and then I can return the sum. So Isn't that nice? So if you ever wanted to take this, you can easily modify this and make it so that you can add things like add elements to lists and do all sorts of fun manipulations. I'm hoping that the slide was on there, man. I'm hoping. My apologies. I think it may have happened again. If not, just hopefully you're following along with the slides. So I want to do some more examples with for loops. So I'm just going to revisit some that we've seen in the past. So this one is involving pictures. So remember this one where we talked about grayscale? Imagine I have it where I give in a picture and I want to make it so it looks like its grayscale counterpart, but I want to use that weighted approach. Now remember we talked about the idea that if I want to convert a picture to its grayscale, I can always take the average of each one of its red, green, and blue components. So I can take the red value. Actually, I should back up. Remember, each color has a color component. So if we're considering RGB or red, green, and blue values, each one is a color component, and we're assuming each one is taking up 8 bits. So at least in what we're doing, I think we're taking up 8 bits. Yeah, it's 8 bits. So my point is that I want to go through, and I want to do this more carefully than just taking the average of the red, green, and blue values, and then assigning the pixels to that value each time, right? So I want to do something a little bit more careful. Now remember, I told you about the idea that our eyes perceive grays and different colors a little bit differently depending on the sensitivity of the color. So for example, red, green, and blue, when we perceive them with our eyes, we perceive the red and the green and the blue somewhat differently in terms of their intensities. So instead of just taking just the average of the red, green, and blue, I'm just going to take a weighted approach depending on how well we perceive that color component. So I'm going to use a little bit of the numbers will look kind of arbitrary, but I assure you they're not. What I'm going to do is I'm going to take each one of my pixels and I'm going to apply it to this weighted approach by getting the red, green, and blue, performing this operation, and then assigning it to be a new color based on what we're calculating. And what we're calculating is really just the luminance of the picture using this weighted approach. So note the luminance you can calculate in the brute force way where you just take the average, or you can do this weighted average approach. So let me walk into the code here. So anyways, I'm given a picture as input. And what I'm going to do is I'm going to update this picture by modifying its pixels. Now remember, I'm being given the picture object. So it means I'm directly manipulating that picture. I'm not manipulating a copy of the picture. I have the actual picture. So when I go through this, notice I have a for each loop. I have for p. Now p is a variable that's going to store each element of my collection. I have in, and I'm going to consider get pixels of picture. Now get pixels gives me a list of all the pixel objects. So it means that P is going to take on each pixel object in my list. So P is going to be a pixel object so that I can get its red, get its green, get its blue as I have here. And I'm going to multiply it by these magnitudes. Then I ultimately compute the luminance by just summing those. And then I simply figure out what the new gray color should be based on the luminance. And then I finally use the setColor function to assign the pixel P the new gray color. Now, as I mentioned, this approach works a little bit better for the human eye when it comes to grayscale than just doing the averaging approach. This typically works really well with photo colors, photos that are taken of actual things, not digital things so much. I find very often, in my experiences at least, that typically is the case. But keep in mind, this isn't the only show in town. There are other ways of doing this. I encourage you to explore more things about image processing. There's always a lot of things to explore. Image processing is a very fascinating thing in its own right. Now, another example I want to talk about is the idea where I have and manipulate sound. Now, you might remember this demonstration from class, and I just wanted to illustrate it using, because I haven't given you a really good example where I have an if statement inside of a loop. I thought this was a good example. So I'm going to have a function called only maximize. I know it's a function because I use the keyword def. And I'm being given a sound object. And what I want to do is I want to go through each sample in the sound object. So if I want each sample object, I need to use get samples. Or I can directly access each sample using a specific one of the functions we've seen in this class. So sample here will take on each one of the sample objects, because get samples gives me a list of all the sample objects. And what it does is it assigns the sample value to this variable called value. And then what I do is I just check if it's positive or negative. If it's positive, then I'm just going to set it to the largest possible value I can set it to without any issues with the representation of the integers. Likewise, I'm going to do the same thing, but negative. Now, you remember, those numbers aren't technically arbitrary. Remember, we talked about the idea of two's complement numbers. So if I give you an integer and I encode it with 16 bits, the first bit of these 16 bits is going to signify the sign, positive or negative. And then I'm going to use the remaining 15 bits to represent the rest of, like, the magnitude of the number. So on the positive side, 2 to the 15 minus 1 is going to be 32,767, and then minus the minus. You can calculate this out. It's going to give you that amount over there. It's for the negative side. And as we've seen, when you maximize it like this, you end up getting it where it takes everything and it goes to the most rather extremes. Now, as you saw in class, it was very strange because we technically maximized all the audio all to its extremes. We took something very normal like that and we made it look really radical. But we could still technically hear the noise. Like, we still hear the original sound, but it was a lot of noise in there. It's because of how we perceive the sounds. Because remember, our sound, like the sounds we perceive, typically are based on the volume or amplitude and the frequency in which they occur. When I do this, when I maximize this, I wanted to point out here that we're not really changing the frequencies that much with the original sound, so that's why we're actually still hearing parts of the sound. Although by raising the amplitude to their extremes, we're kind of introducing noise into the sound, and we're not perceiving those maximized parts correctly, for our ears at least. But that's generally the idea. It's kind of neat. But you remember this from class. It was pretty neat. Remember, I told you, I gave you a bunch of fun sound effects, and I told you, don't worry, I don't want to give you nightmares. This is one of those. So, I want to finish up this class, because those are the main essentials I wanted to talk about. I want to talk about the last bit of this class, and this is more for me to you, and I want to do this because we're at the end of the class, and I really wanted to make sure you got something out of this, because there's a lot of things that we've seen, and there's a lot of things that are all out there still to explore. So what have we seen so far? Now, believe it or not, you've seen a lot of the essentials of programming. So we've seen control structures, functions, variables. We've seen how we can apply these to solve some basic problems like computing the maximum or the minimum, or performing transformations on pictures and sounds and manipulating strings. But that's something that we can do, right? We can do that together, and it wasn't that bad, right? Like it was always, we always have to start somewhere. And like I told you, when everybody starts off at the beginning, there's always places where people make small little mistakes, and that's okay. Never be afraid to have those small mistakes happen, because guess what? You always can learn from them. The only time you do not want to make mistakes is when somebody's expecting you not to make those mistakes. So in a learning environment, it's so much easier to make those mistakes than when, say, for example, you're somehow put into a position where you're designing a rocket or something. You don't want to be in that position where you're making mistakes with your final software. But the point I'm getting at is that never forget to learn, because that is one of the most key things when you're working with programming or software development, is that you're always going to find that new tools will come along, but these fundamentals, a lot of them will not change. But you always have to be flexible. So for example, what can you do? Maybe you can learn another programming language. Oftentimes, learning just one programming language helps you a ton learn another one. That's quite a common thing. Now, you can always try making your own programs, whether they be smaller or bigger. Usually when you're going bigger, I recommend trying and practicing out something. So if you're trying to do something really ambitious, start small. Start small and then work your way up. If you're starting small, remember, you don't have to make giant programs. You don't have to get into hardcore software development. You can if you want to. But remember, programming is a tool. You can use that to solve problems all over the place if you find it appropriate. So remember, programming is a tool. Just pick the appropriate tool for your problem. Sometimes it makes sense to try to use a program to solve a problem that would otherwise take hundreds of hours to do manually. But otherwise you have to ask yourself several questions. Some of the things we talked briefly about, like whether it be like ethical questions or questions like, okay, does it make sense? Costs or benefits? There's all sorts of questions you need to ask yourself about, is it an appropriate tool to use? But generally what I'm saying is, don't let software development or programming seem like it's something that is beyond you. It's always there and you can always try it out. In this class, I've hopefully given you some of the basic essentials so that if you wanted to pick up some of this stuff and you wanted to try using it yourself, you can always do that. So remember, never forget to learn. That's the main thing I want to say. Now, another thing you can do, because remember, you have a lot of the essentials of programming, but oftentimes what comes along with the programming is how we can use the computers to solve problems. And ultimately, that's based in understanding how computing works and why it works and what it is. So that ultimately means if you find a lot of these things very fascinating, I recommend learning more computer science. So I recommend dipping yourself into that mathematical science because it's very broad and there's lots to explore. And remember, it's about solving problems too. But really at its heart, if you find a lot of the things I'm talking about and you want to know why questions and why is it that it always is this way, these are kinds of things that are better addressed in a computer science area. For example, why is there a faster way to solve this problem that we've seen in class? These are things that directly we can talk about in a computer science class. Remember, you got to think about not just as programs, but the procedures, these algorithms of how we can solve the problems. There's a lot of things that I couldn't even show you in this class because there's just so much I had to show you. But that's my main other piece of advice, where to go from here. So if you find yourself interested and you've not considered or have taken 161 or 162, I recommend checking those out. Those are pretty good places to start if you're interested in computer science. So one quote I want to leave you off on when it comes to this is just remember, computer science is not about machines in the same way astronomy is not about telescopes. There's an essential unity of mathematics and computer science. So this is a quote from Michael Fellows. There's quotes like this as well out there. But the point I want to get at is that there is a deep underroot underneath all of this stuff that is fundamentally mathematical. And we've seen a lot of that kind of stuff pop up now and then in this class. If you find yourself very fascinated by these ideas, I recommend checking out computer science. It's very fascinating. So, lastly, I just want to say, so this is just from me to you. So I hope you got something new out of this class. So we've seen how we can use programming to solve all sorts of basic problems with this focus where we looked at different multimedia applications like picture, sound, text, all of these types of things. A lot of the principles, the programming principles underneath them, you can use in all sorts of different languages. It's just a matter of learning the rules of that programming language. For example, if you wanted to use a lot of the things that we did with Jython and JES, and you want to just use it in Python, I'm certain that there exist modules or libraries out there in Python that can do a lot of the same things that we can do here in this class. Or even you can use JES. It's pretty handy. So I hope you had a wonderful time in this class. It was a wonderful time having you in this class. And I want to wish you the best with your future studies and the last bit of this class. So lastly, I wanted to say thank you very much for the opportunity to be your professor, and have yourself a beautiful day.